Okay, so we're going to talk a little bit about changing variables within an integral. And so when would you ever want to change variables? Well, so recall that if you're doing a double integral, you're looking for something like this. So you're integrating over an area region R, a function f, and we'll just say that the function is a function of the variables x and y, and then we're integrating with respect to these small little area regions that we're just denoting by dA. And up until now, what we've done is we've tried to either fix an x coordinate in the region and then seen where y goes between or vice versa. So our region looks something like this. Maybe our region is bounded between two functions of x like this, and so we can just really easily just say, okay, well, here's our first function of x, here's our second function of x, here's our region R and there, and so this integral we can write as the integral from a to b of the integral of f1 of x to f2 of x, and then integrate our function, and then we write this area element as just dx times dy. And we can just think, well, one of these area elements is one little square like this, dA, and then this square is just dx times dy. So we can just add up all of these little area regions, multiplying by the function values there, and everything's all well and good. So let me go back to my first question. Why would I want to change variables? Everything was working so well with the variables x and y. Well, it comes up when the region that you want to integrate over has different symmetries than just, being naturally bounded between a function of x and a function of y. So one go-to example is, what if our region were a circle? What if we wanted to actually integrate over this region here? Now we could do something similar, right? We could actually write this as kind of a region bounded between two functions of x, but there's actually a better way to do it, and that's to use polar coordinates. And so the idea behind polar coordinates is they take these circular regions, and instead of describing them in terms of x and y, they sort of describe these regions as kind of rings going out. So each ring is a different distance away from the origin, and then we're kind of sweeping along an angle like that. So that's kind of the idea. When we have regions that are just more naturally described sort of in circular ways or in polar coordinates, which we'll review in just a minute, it's better if we write this dA, instead of writing it as dx times dy, writing it in terms of different coordinates. But what that requires doing is really changing variables, so changing our function, changing what f is a function of, so we need to replace x and y with the corresponding variable transformations. We need to change dA, and then we also need to change our limits of integration. So it's a rather involved process, but what you'll see is that it will turn integrals that would be very difficult or maybe even almost impossible to do in standard Cartesian xy coordinates into integrals that are very, very simple to do in polar coordinates. And then we'll also extend that idea to cylindrical coordinates for triple integrals, and then spherical coordinates for triple integrals as well. Okay, so before we get into changing variables in an integral, let's just review what polar coordinates are. So as I said before, polar coordinates, instead of just kind of giving an x and a y coordinate, I think about two variables, one being the distance from the origin and the other being the angle formed with the positive x-axis. So to be a little bit more precise, if I have a point in the xy plane, let's say this point here, now I can think about here's its y coordinate, here's its x coordinate, like that, and just go up to it there, go up to it there. So this is the point xy described in Cartesian coordinates. But what I can do instead is say, okay, well, it has a distance from the origin. So let me call that distance r. So let me let r be the square root of x squared plus y squared. But now, the set of points that are the same distance from the origin form a circle. So I'm thinking maybe about this point being on a circle of radius r, like that. So what I also need to do to describe the point is to give an angle. So I'm going to give the angle here from the positive x-axis, like that. So in this way, I can just describe this point, xy, in another way. I can say that x is equal to r, the radius away, how far I am from the origin, times the cosine of theta, so the adjacent side. And then I can say y is equal to r sine theta. Like that, right? Because sine theta is going to be the opposite side, and that's going to give me the y coordinate of this right triangle right here that I'm forming. So that's the idea behind polar coordinates. I'm just, instead of describing a point as xy, I'm describing a point as r theta, where r and theta are given by these transformation equations. So of course, if I have an r and a theta, I'll just find my theta and then go out that far away from the origin, and that's how I would plot a point in polar coordinates. Okay. And polar coordinates are great for describing regions that have some sort of symmetry about the origin. So circles are very easy to describe in polar coordinates. And so just a couple of notes about polar coordinates. Notice that we essentially have a version of the Pythagorean theorem, that x squared plus y squared equals r squared. So that's really useful to keep in mind. And so this is a way, we can just solve for r. I can just take, if I have an xy coordinate, I can just square the x component, I can square the y component, and then add them together. That gives me the square of the radius. And then the angle, now I have to kind of think about which quadrant I'm in, but you see that I can find the angle by doing maybe the tangent ratio. So if this point is away from 0, if it's somewhere out here with r positive, I can just say that the inverse tangent of theta is equal to y over x. Sorry, theta is equal to the inverse tangent of y over x, right? If I wanted to find theta and I knew y and x. So probably the most important thing about polar coordinates is how to describe area regions. Now recall that in Cartesian coordinates, if we had a small area region like this, we could just say that it was dx times dy. So what if I wanted to describe a small area region in polar coordinates? Well, let's look. So there's one thing that's a little bit tricky. So let's say I have a small little area region in polar coordinates, like that. So here we go. So here's my little area region, dA. And now notice that relative to the origin, the angle here changes by just a little bit. If I have a little piece of area, then it's lying between a small little change in the angle theta, so d theta. And then the width This way, the direction that's kind of going out away from the origin has a width dr. Now you can say, okay, well if the area region in Cartesian coordinates was just dx times dy, maybe the area region in polar coordinates is just dr d theta. But there's one problem, because the farther out I go, this change in theta actually gets magnified. So if I'm closer to the origin, a small change in theta sweeps out a smaller area than if I'm further away from the origin. And actually there's another problem, because theta really is dimensionless. Angles are dimensionless. So actually what I need to do is actually the width, if I just kind of think about the arc length formula, the width of this piece here is really given by r times d theta. So the arc length along an arc on a circle of radius r making an angle of theta is r times theta. So if I have a little change in theta d theta, this width here is really r d theta. So if I look at a little area region, on the one hand it has width dr, and then it has length r d theta. So dA in polar coordinates is really equal to r dr d theta. So when you're doing the change of variables, instead of putting in dx dy, I want to replace dx dy with r dr d theta, which actually adds in a variable r into the integrand. So it's going to actually interact with the function that you're integrating. Okay, so let's say that we have a region, R, and we are integrating a function, f of xy, dA. We're trying to find this volume underneath the graph of the function that is f. Then we look at the region, and let's say we decide that it's going to be easier to compute the integral in polar coordinates. So there's some sort of symmetry about the origin, or it just kind of has a nice circular shape, or we just sort of make some observations that say, okay, we want to change variables to polar coordinates. So what we're going to do is we need to change three things. So the region, first of all, we need to describe in terms of polar coordinates. So that's supposedly going to be easier, changing to polar coordinates. But what do we do with the function in dA? So let's look. So let's say our region looks something like this. And so the way I'm drawing this out here, let's say this is a function of theta, and this is another function of theta. So the output of these functions are actually the radius r. So for a fixed theta, my r is going from f2 of theta to f1 of theta, like that. So then what I'm going to have is, well, theta is going to go from, say, if this is alpha, and this angle here is beta, so this angle all the way to this angle, that. So the angle, say, is going from alpha to beta, and then for a fixed angle between alpha and beta, here's alpha and there's beta, r is going from this function of theta, f2, to this function of theta, f1. So f2 of theta all the way up to f1 of theta. All right, and then what do we do with the function f? Well, we can't leave it in terms of x and y because we're changing to the variables r and theta. So what do I need to do is actually, instead of putting x, put r cosine theta, because that's what x is. And then for y, I need to put r sine theta. So I've redescribed the region in terms of polar coordinates. So I fix an angle and then see that the region is naturally between two functions of theta. And then we have r, dr, d theta. So recall that the dA we replace with this new area region, r, dr, d theta, and then the function we replace x and y with their corresponding transformations into polar coordinates, and now we have the polar integral set up. And it's going to be through examples that you're going to see exactly when you should switch to polar coordinates. You know, when the region is a circle or it's some sort of, it has some sort of symmetry about the origin, so that you can kind of bound the region between two functions of theta for fixed thetas between maybe two bounds like that. Okay, so the final coordinate transformation we want to talk about is changing to spherical coordinates within an integral. So again, we're starting with a triple integral over some region of a function, and then we have our volume element here. And so we have dv is dx, dy, dz in Cartesian coordinates. But for spherical coordinates, what do we want to notice? Now for cylindrical and polar coordinates, we just notice that there are actually symmetries sort of around the z-axis. So kind of rotational symmetry around the z-axis. For spherical coordinates, we really want to notice some sort of spherical symmetry. And now let me just review a little bit about what spherical coordinates are before we talk about how to actually make the transformations. So mostly we just really need to know, well, how do we transform x, y, and z? And then also, how do we describe a volume element in spherical coordinates? So what we want to do is take our point x, y, z here. And now instead of kind of projecting it down and just using the z-coordinate, what we want to do is we want to just straight up take the distance from the origin. Now notice that the r was the distance in the xy plane from the projection of the point onto the xy plane. But here we want to use this variable rho to really mean literally just the distance from the origin to the point. So rho really is just the square root of x squared plus y squared plus z squared. Okay, so now that we have this coordinate here, rho, the distance, well, we need to give it some kind of orientation because rho can kind of move around, and actually points with the same rho value will make up a sphere. And that's kind of what we're getting at with the spherical coordinates. So we want to kind of fix the spherical distance and really think about regions between different spherical shells, and then we need to kind of rotate in different angles. So we're actually going to need two angles to describe the spherical coordinates. So the first one is phi. And phi is the angle that the point makes right here with the positive z-axis. Okay, and so why is the positive z-axis? Well, it's just really by convention at this point. There's not really, you could have made it from the y-axis or something, but phi is just the angle that this ray passing through the point makes with the positive z-axis. Okay, so we also need another coordinate. So if you think about, all right, well, I can have all of the points with fixed radius away, rho, and then also having a fixed angle with the z-axis, but there's sort of a rotation you can make around the z-axis that would describe points that have the same phi and rho values, sort of making a cone. So what we also need to do is we need to fix the angle of rotation about the z-axis. But this is exactly the angle theta that we had before. So if we look down at the projection of this point into the xy plane, like that, then this angle theta really is the theta from the positive x-axis that we had before. So how do we convert from, say, x, y, z coordinates, Cartesian coordinates, into spherical coordinates? Well, what we want to do is look at, okay, first of all, make a couple triangles. And so the z coordinate here, so right here, is going to be rho, and then we're going to use cosine of phi. Because it's the adjacent side here. Okay. And now for x and y, we can actually sort of use r to get x and y again. So if you notice that rho times the sine of phi is really giving me r. So that's another useful observation, is that r is really rho. So r in polar coordinates is rho times sine of phi. And then from there, we can get x. So x is r cosine theta. So x is rho sine phi and then cosine theta. And then y is rho sine phi sine theta, like that. So that's how we get x, y, and z from rho, phi, and theta. Okay, so it's a little bit more complicated than polar coordinates or cylindrical coordinates, but that's what it is. Okay, so then the question becomes, all right, well, we can set up the triple integral by saying, okay, well, the two angles will just be bounded between two angles. So let's say that theta is bounded between alpha and beta. And then phi is bounded between, say, let's just use gamma and delta. So these are angles, just kind of fixed angles that, for simple applications, these will just be, ranges of angles that phi and theta can take. And then the real action is we want to notice that the region kind of lies between two functions of phi and theta. So maybe f1 of phi and theta, and then f2 of phi and theta. And then we have our function, which we will then have to convert. So we'll have, we'll actually plug in what x, y, and z are in terms of rho, phi, and theta. So it'll be rho sine phi cosine theta, and then we'll plug in rho sine phi sine theta for y, and then we'll plug in rho cosine phi for z. So that's what happens to our function. And then what happens to dv? This is where the magic happens. So let me just tell you the answer. So dv becomes rho squared and then sine phi d rho d phi d theta. And of course these can be switched around, but this is really what dv is. This is what we want to replace. Instead of putting dx, dy, and dz, we put rho squared sine phi d rho, d phi, d theta. And then this is the setup. So you see that this rho squared sine phi actually becomes part of the integrand. And again, I mean, this seems like a mess to do, but the payoff is that you're doing this integral transformation on a region for which the bounds get simpler. And remember, the hardest part about triple integrals is really setting up the limits of integration. So you only do this when switching to spherical coordinates greatly simplifies setting up the limits of integration. And we'll see some examples that will hopefully help you begin to see when you should switch to spherical coordinates and how exactly the machinery takes place once it gets started. Okay, so the last thing I want to do is I said on the last slide with spherical coordinates that a volume region in spherical coordinates is rho squared sine phi d rho d theta d phi, or d phi d theta, doesn't really matter. And so I want to try to give you at least a snapshot picture of where this comes from. So if we look in three-dimensional space, and I look at a region. So first of all, let me look at a small change in phi. So if I have phi coming out here, and then phi coming out here, so here we have d phi. Just like with d theta in polar coordinates, the further out I am, kind of the greater the width this is going to take. So if I really look, so if here's my region right here, if I look at this width here, this really is like an arc length given by r times, rho times the change in phi. So r d phi is kind of the width of this rectangle, and then this distance here is really d rho. Like that. So it's really d rho by rho d phi, sort of for the same reason that it was dr times r d theta. Okay. But then we also have a small change in theta. And the best way to view this is to actually project the region down into, so here's the region that I kind of draw out. So there's my volume region right there. So if I project this down into the xy plane, notice that a change in theta really is the same as it was in polar coordinates. So this last dimension here, right there, projected down, really is the same r d theta. So the dimensions of this sort of rectangular region described in spherical coordinates are d rho, that's kind of the change away from the origin. Then there's rho d phi, that's the change in phi, and again I just need to multiply by rho to account for how far away I am from the origin. And then r d theta. But what is r? R is actually equal to rho sine phi. So if I put this all together, dv should be, well, rho sine phi, and then times rho d phi times d theta times d rho. So all in all, I get rho squared sine phi, and then d rho d theta d phi. And that's kind of just a geometric picture of why this volume region is described in this way. Now there is a kind of more rigorous algebraic way to see actually that this rho squared sine phi is something called the Jacobian of the transformation, but that really is best described in kind of a rigorous treatment of variable transformations, which we're not going to do here. We're just going to specifically just mention the transformations polar, cylindrical, and spherical coordinates because they really are the most common. Okay, so I want to transition into talking about triple integrals. And the first thing we're going to talk about with triple integrals is cylindrical coordinates. So the idea behind cylindrical coordinates is that the z coordinate, we're not going to change. Okay, so we're thinking about a three-dimensional coordinate system. Here's x, y, and z. Okay, and so for a point, x, y, z, instead of just describing them as the Cartesian x, y, z coordinates, the z coordinate we're really going to leave alone, but we're going to project the point down into the xy plane and describe sort of the x and y coordinates in terms of polar coordinates. So instead of having x, y, z, we're going to have r cosine theta, r sine theta, z to describe the region. And the way we'll do that is we'll just put a triple r, theta, and z to mean, okay, if this is the point r theta z right here, well, we go out a distance r from the origin in the xy plane, make an angle with the positive x-axis of theta, and then go up z units, and that'll be our point. So that's how we describe points in cylindrical coordinates. Okay, so how do we actually implement this in an integral transformation? So if we have our integral over a region, and now the keyword here is cylindrical, so if we notice our three-dimensional volume region has some kind of cylindrical symmetry, or basically symmetry about the z-axis, then we may want to try to describe the region using cylindrical coordinates. And the way we do that is very similar to how we did with polar. So remember that in Cartesian coordinates, this dv was dx, dy, dz. And that's going to be for some little box, little volume element in space. It's going to have width dx, length dy, and height dz. Well, the height here we're not changing, but the little area region of the bottom we're instead describing in terms of polar coordinates. So actually dv in cylindrical coordinates becomes r dr d theta dz. And the region looks more like this. So it kind of has a polar shape. So it's still sort of like rectangular prism shape, but the edges are kind of curved in like that. So this is kind of a little cylindrical region. And you can see if you sort of rotated this around the z-axis, it would make a nice cylindrical shell. And so a lot of times when we're doing cylindrical coordinates, we're doing things like finding the mass of cylindrical rods, or finding the moments of inertia around, kind of a central axis, and we're kind of looking at cylindrical shells that we're approximating have approximately the same distance from this axis of rotation, or something like that. So that's the idea. So then the final product, what we get is, okay, well, we'll again have theta just be between two angles alpha and beta, and then our r coordinate is going to be between two functions of theta, and then z is going to be exactly the same. So z is still going to be just, so g1 of xy, g2 of xy. Now we're saying xy here, but really we're going to, after we do the z integral, convert them into polar coordinates, x and y. And then we'll have f is going to be not x, but r cosine theta. And then y will replace with r sine theta. And then z will leave alone. And then we'll have r dr d theta dz. So that'll be the process. We change the limits, and now this will be a lot of work, or it seems like a lot of work, but we're doing this work to more easily describe the region, make it easier to integrate. And then, of course, this is the price we pay. We have to replace x and y with r cosine theta, r sine theta, and then we pick up this factor of r from doing the change of variables of the volume element. All right, so we're going to do our first integral where we convert to polar coordinates. Okay, so I think it's worth spending a little bit of time just thinking about why we're going to convert to polar coordinates, first of all. So if you look at this, you say, okay, well, first of all, what is an annulus? Well, it's this. Okay, so an annulus is kind of like a donut in the plane, anyways. And so let me just sketch this region and kind of describe why we might want to switch to a different coordinate system other than just the standard XY coordinate systems. So this region is in between two circles, one of radius 1 and one of radius root 2. Okay, so here we have the unit circle. That's like here. That's x squared plus y squared equals 1, so we're greater than that. And then here we have, on the outer side of the annulus, x squared plus y squared equals 2. That's a circle of radius square root of 2. And this is a circle of radius 1. And so the region is really in between here. So you see it's exactly what I said. It's a donut, but flat in the plane. Okay, so notice that if I tried to do my old tricks and say I fix an x-coordinate, say here, look at the y-coordinate. So the y-coordinate is first going to go from here to here, but then it's going to go from here to here. And actually it's different if I fix an x-coordinate here. My y-coordinate is just going to go from here to here. So you see that it's not quite as simple to just say, okay, well I fix an x-coordinate and then y is going between two functions of x. Well actually there's really four functions of x here. There's this bottom, the minus square root of 2 minus x squared. There's the minus square root of 1 minus x squared. There's the plus square root of 1 minus x squared. And then there's the plus square root of 2 minus x squared. So there's a lot going on here. Okay, so you could try to do it in Cartesian coordinates, and maybe that's a good exercise. But I think it's more valuable to just see how polar coordinates simplifies this problem tremendously. And you may ask, well, why do I want to use polar coordinates? How do I know I want to use polar coordinates? Well, I want to use polar coordinates because there is a lot of symmetry about the origin in this region. You see that, if I take kind of a slice, I get the entire thing by just rotating around the origin. And that's exactly what polar coordinates do. They just give you a set distance and then you kind of rotate around the origin like that. So let's just see what happens. Okay, so remember that if we write down our double integral, so R is this annulus region, and then we have f as a function of x and y, and then dA, this is what we're looking for. And so we could try to describe the limits of integration in terms of x and y and put dA is dx dy in whichever order we're doing the iterated integral. But let's think about doing it in terms of polar coordinates. So if I look at this region, let's think about how to describe the region. Well, if I fix any theta, so let's say theta is here, then notice that R is going between 1, radius 1, and radius 2. But then where am I fixing an angle? Well, I'm going all the way around the circle. So theta is between 0 and 2 pi. So for theta between 0 and 2 pi, R is going between 1 and 2. Look how easy it is to describe this region in polar coordinates. This is essentially a rectangle in polar coordinates. Theta is just going from 0 to 2 pi because I'm going all the way around. And then for any fixed theta, r is going from 1 to 2. Well, that's amazing. So let's see what happens when we plug in our function. Now the function is x squared, but we're converting to polar coordinates. So x in polar coordinates is r cosine theta. So my function is x squared. So the function here is r squared cosine squared theta. Okay, so that's just literally x squared right there. And that's the function that I'm integrating. But I need to put it in polar coordinates. I need to put everything in terms of polar coordinates. The dA I need to put in terms of polar coordinates. So remember that dA in polar coordinates is r dr d theta. Okay? And as I said, this r that picks up when we change variables in the dA actually becomes part of the integrand. So we can rewrite this as 0 to 2 pi, 1 to 2 of r cubed times cosine squared theta dr d theta. And this is just a regular iterated integral like we've seen before. We first want to do the inner integral with respect to r. So I just need an antiderivative of r cubed, which is r to the 4th over 4. So what I get is 0 to 2 pi, and then I have cosine squared theta. That's just a constant in the inner integral, so I can pull that out. And then I have r to the 4th over 4 evaluated from 1 to 2. Okay, well let's see, 2 to the 4th is what? 2 to the 4th is 16, so 16 over 4 is 4. So I'm getting 4 and then minus 1/4. Okay, well 4 minus 1/4, what is that? So that's 16 over 4 minus 1 over 4, so it looks like 15 over 4. So it looks like I have 15 over 4 just from this evaluation here, and then times the integral from 0 to 2 pi of cosine squared theta, d theta. Okay, so now I just have a regular old single integral. Now this one is a little bit tricky. So cosine squared theta, how do you integrate cosine squared theta? Well, you need to use a trig identity. So the trig identity we're going to use is that cosine squared theta is what? Well, if you pull up, I can never remember trig identities. I always encourage you to look them up if you don't know them. They're very hard to remember if you're not kind of used to using them. So what we have is that yes, cosine squared theta is the same thing as 1 plus cosine of 2 theta all over 2 d theta. Okay, so this is just a good calc review. And so we can factor this 2 out, and so we'll have 15 over 8, and then we integrate from 0 to 2 pi of 1 plus cosine 2 theta d theta. Okay, so I can integrate 1. So I just take an antiderivative, I get theta, evaluate from 0 to 2 pi. But cosine 2 theta is a periodic function, and I'm actually here going to be integrating it over 2 of its periods. So this is actually going to give me 0. So my final answer is just 15 over 8 times 2 pi, or 15 pi over 4 will be our final answer for the integral. Okay, so this is a triple integral problem. Okay, so this is an example of a problem where we're going to be doing a triple integral and just integrating the function 1 to find the volume of a region. So more or less we're just integrating, doing a triple integral over this region that's described here. We'll talk about that in a second, of the function 1, and then we're just adding up all of the volume regions that we want to describe. So if we describe them in Cartesian coordinates, it would just be dx, dy, dz, and then we would want to make sure that our limits of integration were, in terms of x, y, and z, accurately describing the region. But that's going to be a little bit difficult. And here it's not impossible. I'm not saying that it is impossible to do this using Cartesian coordinates. I just want to illustrate that sometimes it's easier to use cylindrical or spherical coordinates. And in this case, it's really cylindrical. And now, one way to think about cylindrical is that you're doing everything the same with respect to z, but when you get down and evaluate the first iterated integral, you're just using polar coordinates to describe the region in which you're kind of fixing an xy point and then letting z vary. Okay, so let me show you what I mean. So notice, first of all, that if we just kind of do it the way we've been thinking, for a fixed x and y, z really is going from this function to this function. So the first step of my integral really is just saying, okay, well z is going from 4x squared plus 4y squared up to 4. And then I'll just put dz, okay? And then the next thing I would want to do is just describe, okay, well this is for a fixed x and y in some region in the xy plane. Okay, so let's see what that region is in the xy plane. Well, the values of x and y that I can fix to allow z to vary between these two surfaces are going to be the xy points between their intersection. So if I set these equal, so if I set 4 equal to 4x squared plus 4y squared, then what I have is just the unit circle. So actually, kind of the domain of x and y, where I'm fixing an x and y here, is just the unit circle, like this. So somehow the projection of this region down onto the xy plane really is just the unit circle. And anytime that happens, the unit circle is really easy to describe in polar coordinates. So what is it? Well, r goes from 0 to 1 for any fixed theta, and theta goes all the way around the circle from 0 to 2 pi. So what I can do is then just say, okay, I want to integrate from 0 to 2 pi for fixed theta, and then let r go from 0 to 1. And then we have r dr d theta, because again, we're converting to polar coordinates. So kind of sticking with the theme that z stays the same, we can do exactly what we want to do with z. So what do we get? Well, we're just going to get z evaluated from here to here. So we'll have everything the same on the outside. Integral from 0 to 2 pi, integral from 0 to 1 for r and theta. And now what we're going to get is 4 minus 4x squared minus 4y squared. And then we have r dr d theta. Okay, so here's where we really need to dive in and convert into polar coordinates. All right, so let's see what's going on here. So notice that these outer limits of integration are in terms of r and theta. So we really need to make sure that our integrand is all just in terms of r and theta. Well, here's r. 4 is okay. But now x and y, I really need to convert to polar coordinates. So notice that we can be a little bit crafty here. And 4x squared plus 4y squared is the same thing as 4r squared. So 4x squared plus 4y squared really is just 4r squared, like that. All right, and so what we have is integral 0 to 2 pi, and then integral 0 to 1 of 4 minus 4r squared times r. And then we have dr d theta, like that. And now we have everything in terms of just r and theta. This is just a standard iterated double integral. Alrighty, so how are we going to do this? Well, here's where our techniques of integration come in. So I can multiply this out and take an antiderivative, but I'm going to do something, well, maybe a little unnecessary, but it's a good technique to remember. I'm going to do a u substitution. So here I'm going to let u be 4 minus 4r squared, so that du is minus 8r dr. And so notice that that means r dr, which I have right here, is du over negative 8. So I'm going to get a factor of negative 1/8, but other than that, the substitution is going to work really nicely. So let's go over here and actually do it. So we have the integral from 0 to 2 pi. And now we need to change our limits. So notice that when r is equal to 0, we have u is equal to 4. And when r is equal to 1, u is equal to 0. We have, so recall our negative 1/8 we pick up from the substitution. So negative 1/8, just leave that out front. And then we just have u, and then du d theta. Alrighty, and so what is this? Well, I have a u squared over 2, and then I evaluate it from 0 to 4, so that's going to be 8, essentially. Well, negative 8, because it's going to be 0 minus 16 over 2, so negative 8. Well, that cancels with the negative 1/8 that's out here. All right, so what do we have? We have negative 1/8 times, here let's just go ahead and write out all these details. So 0 to 2 pi, and then here we have u squared over 2 evaluated from 4 to 0, which I said is just going to give us negative 8, and then d theta. So this is really just going to be the integral from 0 to 2 pi of just d theta, which is 2 pi. So that's the volume bounded between these two regions. Alright, so we have another function of 3 variables, and we want to integrate over this region bounded between z equals 0 and this sphere x squared plus y squared plus z squared equals 1. And I'll just tell you, kind of the punchline is because a sphere is coming into play, we're probably going to use spherical coordinates. And in fact, the region we're integrating over is half of the sphere. So, I mean, that's your red flag to use spherical coordinates. Okay, so let's think about how we would set this up. Well, we're looking at the upper hemisphere up here. So if this is x, y, and z, I'm going to try to kind of roughly draw this. So there's kind of the top, and then in the z direction, we have something like that. Okay, so it's the upper half hemisphere. And the more I draw, the more it's going to be kind of a disaster. But if you're lost on what I'm drawing, just go cut a basketball in half and stick it on the table. Okay, so the point is we just need to kind of bound this region R. Okay, so we're looking for this triple integral over the region. And the first and hardest step is always just to describe the region using the limits of integration. And then we'll plug in our function. Of course, we'll convert everything to polar coordinates. And then we'll have our volume element that we'll need to write again in terms of polar coordinates. Okay, so let's look at the angles, or let's look at the radii. So the radius on this hemisphere is going from 0 all the way to 1. Now that's for a fixed phi and a fixed theta. So for a fixed phi and theta, r is going from 0 all the way to 1. The center of the hemisphere out to the edge of the hemisphere. So rho is just going from 0 to 1 is the point. Great. Okay, so what about phi and theta? Well, phi starts at 0, which is the z-axis, and it'll go all the way down to the xy plane. Well, that's just 0 to pi over 2. So phi is going from 0 to pi over 2. And then for theta, theta is going all the way around to give me the whole hemisphere. So theta is going from 0 to 2 pi. Okay? And now let's see. Our function is x squared plus y squared, but that's equal to r squared. And recall that r in polar coordinates is rho sine phi. So actually our function is just rho squared sine squared phi. So that's our function, which is x squared plus y squared. But I'm converting to polar coordinates. And then I have to add in what the volume element is. Well, that's rho squared times sine phi. And then let's get the order right. So we had d rho first, and then we went to phi, d phi, and then finally d theta. All right, so now we've set up this triple integral in polar coordinate, or not polar coordinates, spherical coordinates. So it's really not so bad when you get the hang of it. I mean, it would be hard to set up an integral in spherical coordinates if it wasn't natural to set it up in spherical coordinates. But because this is naturally a spherical region, it's really not that crazy to just kind of describe the region in spherical coordinates and then just kind of fill in what the volume element is, and then just write the function in terms of spherical coordinates. Okay, so let's think about actually evaluating this integral. All right, so we're going to do rho first, and essentially we're just integrating rho to the fourth. Okay, so we have 0 to 2 pi, that's theta. And then I'm actually going to factor out this sine cubed phi because it doesn't affect the inner rho integral, but I got to keep it inside the phi integral, of course. So sine cubed phi, and then we have 0 to 1, rho to the fourth, d rho, d phi, d theta. And then this is a walk in the park. So an antiderivative is rho to the fifth over 5. I'm just evaluating from 0 to 1, so that just gives me a factor of 1/5. And that's, again, I'm just saying this inner integral gives me 1/5. So I'm just going to put 1/5 all the way out. It's just a constant. Then I have 0 to 2 pi, and then I'm integrating from 0 to pi over 2 the function sine cubed phi. And here we have d phi and d theta. So how do we integrate sine cubed? This is a good Calc 2 question. Well, what we want to do, I'll do it up here. So what we want to do is we actually want to do a u substitution, and we want to let u equal cosine phi. Okay, So why in the world would I do that? Well, first of all, notice that du is negative sine phi, d phi. But also notice that u cubed, not u cubed, sine cubed, I can write that as 1 minus cosine squared phi, so in other words, sine squared, times sine of phi. And so you see that actually I can write this as 1 minus u squared sine phi, but the sine phi is going to be absorbed when I do the substitution. I'm just going to get a negative sign. Okay, so sine cubed becomes 1 minus u squared and then minus du. So I get a minus, which I'm hoping will resolve itself because I should get a positive answer. And then I integrate from 0 to 2 pi in theta, and then I have, all right, let's see where u goes between. U is going from, well, cosine of 0 is 1, and then cosine of pi over 2 is 0. And we have 1 minus u squared du, and then we still have our d theta, like that. All right, and we'll keep going. So this 1 minus u squared becomes u minus u cubed over 3, evaluated from 1 to 0, which is, okay, so I'm going to evaluate at 0 and get 0, and I'm going to subtract. So I'm going to have 1/3 minus 1, because I'm going to have a minus quantity 1 minus 1/3. So that's just 1/3 minus 1, which is negative 2/3. But that's great because that'll multiply out here and give me a 2 over 15. So negative 2/3 times negative 1/5 gives me 2 over 15. And now all I'm left with is this theta integral, which is constant. So I just pick up a factor of 2 pi, and I get 4 pi over 15 is the value of this integral. Okay, so we have one more integral, and you can already see, spherical coordinates going on here, but it's just a matter of describing the region. And one thing to notice here is that, okay, so, well, maybe you can or cannot visualize this region, but we have rho is equal to 1, so that's just a sphere of radius 1, and then a sphere of radius 2. So I'm going to draw the cross section here in the, let's see, the z x plane. Okay. So the circles, the cross section, or sorry, the spheres are going to have circle cross sections. So here's like, maybe I'll do it in colors. So here's like rho equals 1. And then here we have rho equals 2. Okay, and then phi is going to cut, so at an angle of pi over 6, like that. Here's my cone. And now you should think that all of this is going to be rotated through an angle of 2 pi about the z-axis and form the actual region. But you see that the bounded region is up here. Okay, so we kind of rotate it around, and it's like a little disc thing up in the sky. That's the best I have. But the cross section really tells you everything you need to know, right? So this angle here is phi equals pi over 6. So it's forming like a cone there when the angle made with the positive z-axis is pi over 6. Okay, cool. So I think this one is pretty straightforward to just go ahead and set up. Notice that there's really no restriction on theta. So theta is going to go just from 0 to 2 pi. And we can sort of do that last. And that happens a lot. Not to leave theta out, but theta ends up sort of being just going from 0 to 2 pi a lot. Okay, so we're going from 0 to 2 pi. And then phi is going from, okay, so minus pi over 6 to pi over 6. So that's the angle phi. Oh, I'm sorry, no. Phi is going from 0 down to pi over 6, and then we're rotating to get the other branch. There we go. So phi, all of this is really in between an angle of 0 and pi over 6 with the positive z-axis. So 0 and pi over 6 for phi. And then rho is going from 1 to 2. Great. So again, I mean, because this is kind of a naturally spherical region, describing it in terms of the limits of integration is really straightforward. But now we need to convert our function to polar coordinates. Okay, so this is going to be a little bit interesting. So we have x equals, just recall, rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. So we're just going to multiply all those together. And what are we going to get? We're going to get rho to the 1, 2, 3 cubed. We have a sine phi squared. So sine squared phi. We have 1 cosine phi. And then we have sine theta cosine theta. And then we have the volume element, which is rho squared sine phi d rho d phi d theta. Bam. Okay, so that is the setup for the integral. So it's naturally pretty easy to do the limits of integration in spherical coordinates. And then everything just gets converted to spherical coordinates. Everything. And now this integral looks like a disaster. And I don't blame you for not wanting to do this. However, if you're clever, you can see what the answer to this integral is immediately. And the answer is 0. Okay, so why is this integral 0? Well, this is kind of going back to the idea of switching the order of integration, which I'm allowed to do. Even in spherical coordinates, I can still switch the order of integration because, you know, these functions I'm dealing with are great. So what integral do I really want to do first? If I do rho first, it's going to be kind of messy, and then phi is going to be kind of messy because I have sine cubed phi and I have a cosine phi. Look at theta. Little old theta down here not doing anything. Well, I have a sine theta and a cosine theta in the integral. Let me just switch the order of integration. So what I'm going to do is I'm going to put phi last. And because none of the limits actually depend on any of the variables, I can just sort of mix and match all I want. And let me put all of the phi stuff out here. So that's sine cubed phi times cosine phi. And then I have my rho integral, and I'll leave my rho to the 5th in there. And then I'll put my theta integral front and center. Sine theta, cosine theta. And then what do we have? I'm doing theta first, then rho, then phi. Okay, so why did I do this? Well, I'm doing this integral first. And now maybe you're starting to see the clever thinking. I know that this integral is 0. And why do I know this integral is 0? Well, I could just do this integral and get that it's 0. But I don't even need to do it, right? Because sine theta is a periodic function. It has period 2 pi. Cosine theta is a periodic function. It has period 2 pi. I know that if I integrate sine over a period, I get 0. If I integrate cosine over a period, I get 0. Well, it's also true that if I integrate the product sine theta, cosine theta over a period, I get 0. So this integral is 0. But then I'm integrating all of this nonsense, but it doesn't matter because what have I factored out of the integral? I have 0 times just a mess of stuff that I could do if I wanted to, but it doesn't matter because whatever I get here, I'm multiplying by 0. So the entire integral is 0. That's as good as it gets.